So we're ready to start. This week we'll say a few words left over from last week on the TTL field, and then we'll study the MAC layer. So just a few words on the end of last week's module. We have seen already the IP header. This is the version for IPv6, which contains, as we know, the source and destination addresses, and also a field of interest now, which is called the hop limit. IPv4 has a similar thing called the time to live. What is this? Well, the time to live originally for IPv4 was really a time to live. That meant in the 70s when an IP packet was sent, all the routers were supposed to count how much time the packet has spent going through themselves, and then if the packet becomes too old, delete it. So a packet had a time to live of a few seconds, for example. The name time to live comes from there, but the correct name is a hop limit, which is the name it has in IPv6. It works in the following way. It's an 8-bit number, so it can be between 0 and 255. 0 is an invalid value. And when you receive an IP packet, you have to inspect this field and take a decision if it happens to be 1. So this field is always decremented as a packet is forwarded on the internet. When it gets 1, we're close to the invalidity, so the only good thing that could happen is if the TTL or the hop limit is 1, is you are the final destination. If you are not the final destination, you will need to send it further, and whenever you send it, the major rule of manipulation of HL, of the hop limit or TTL, is that every router, in principle, decrements it by 1. When I receive an IP packet and I forward it further, I decrement its value by 1, in principle. Which means that when I receive a packet and I can decrement it by 1, which means if its value is larger than 1, then I decrement and forward. If it's equal to 1, and this packet is for me, things are fine, no problem. But if it should be forwarded, when forwarding it, I should set the value to 0, which is invalid, which means I should kill this packet. This is the principle. At the source, when an IP packet is generated by a host, you can put any value you want. You can program with the socket interface to put any value you want. If you don't do anything special, there's a default value, which is currently 64. So here I've broken the philosophy I tried to say. I've explained you how it is working. Now try to reverse engineering. What is it doing? Why do we have that? Yes?
That are just wandering around the network indefinitely.
So that we don't have packets that circulate in the network indefinitely, and that's exactly the main reason. So the internet is supposed to be made of routers that have routing tables, and the routing tables should be consistent. If a router says go to the left and the next router says go back to where you come from, then the packet will be caught in a loop. Loops, of course, in principle, don't exist. But like any software-based system, they can exist. They can exist due to bugs. Some router somewhere is not properly configured. They can exist also because the routing tables are not cast in stone. They change once in a while because the topology changes, because a new router is added, because a link has failed. So they change. And the changes are typically not synchronous. There's not like a big button like we will have when we use Mininet in the labs. We can implement something everywhere in all the routers practically at the same time. But when you're a large-scale network, this is not how things are. If things change, and we will see how they change when we study routing protocols, they change not everywhere at the same time. So there might be periods of time where there are inconsistencies that cause loops. Now you could tell me what's so bad about a loop. So I'm asking you, what is so bad about a loop? What would be the problem of having packets that are caught in a loop? Yes? It creates congestion. Exactly. It can kill the network. It depends on the ratio between transmission and propagation time. If the propagation time of the loop is small and is the same order as the transmission time, which you can, using the values we've seen 2 weeks ago, you can easily forge cases where that would happen, then a single packet that is looping can eat the loop. So the time it takes to transmit this packet is just the time it takes for the packet to come back. So a single packet makes a series of links 100% utilized. So you have a part of the network that's busy sending one packet in the worst case. In other more realistic case, perhaps a few packets. So a loop is a very, very efficient way to do a denial of service attack on the internet. If you can create a loop somewhere, minuscule amount of traffic will populate the network at 100%, making the link unusable for other traffic. So this is the motivation for having this TTL. So it's a safety mechanism. What does the value 64 mean? What does it tell us about the internet? The most we can have to go is 64 hops. So it's the depth of the internet. So we think today the internet is less deep than 64. And it's probably 64 is a safe upper bound. We have used the TTL or the hop limit field in the labs already when we use trace route. The trace route version, so the Unix version, tries to find what is the path to a given destination, and it uses the TTL. So what it does is, if you do a trace route to www.google.com, what the trace route program does, it sends a sequence of packets to that destination, here UDP packets to the echo port, that will have increasing TTL or increasing hop limit. So the first packet will be sent with hop limit equal 1. Which means it will be sent to the next router, and the router will try to forward it and say, oh, I can't forward it. So it will say, this is an invalid packet. This packet is too old, has been caught in a loop or something. And by default, when you receive a packet that has exhausted its hop limit, you are asked to send an error message back to the source to help the source in presumably adjusting the hop limit. You put a value that's too small for the depth of the network you're trying to traverse. Not all routers do that, but many do. So here, this first router did it and sends an error message back to my traceroute program. The traceroute program analyzes the source of this error message and concludes this is the first hop on the route. So it has received an error message from this IP address. Then it prints the name of this router. The name is not in the packet. How did it get the name here? By going to reverse DNS. So it used the directory service. The name is not included in the packet exchange, as we have already seen. So it has received an error message from this IP address, and it goes to the DNS to do what is called a reverse lookup, find what is the DNS name that corresponds to this IP address. And then you continue with hop limit equal 1, 2, 3, etc., until you reach the final destination that will respond to your TCP, to your UDP echo request. And when you get a response, you terminate. So we see here that we're leaving we'll do 3 hops inside EPFL. Then we are in the switch.ch network, which is the network that provides ISP, the ISP for Swiss universities. And we see that Google is directly connected to this network at a location called SwissIX, which is a Swiss Internet Exchange point, probably in Zurich somewhere. When we do that, we get one path. Are we sure that this is the path followed by all the packets that I may send from me to google.com? No, we're not sure. If there are multiple paths, if there are parallel paths, there can be parallel paths, usually there are. If there are parallel paths, then each of those results come from a different packet being sent. So it may be that the system is inconsistent. Perhaps hop number 7 used the left path, and hop number 8 used the right path. So perhaps they are inconsistent. So we're not sure that we are really recreating an exact path with this mechanism. If you want to have an exact path, you probably need to do it a large number of times. And I will conclude this section with this question that I'll let you discover and answer using SpeakUp. I close the poll in 5 seconds. And as you can see on your screen, the majority votes for B, which is the correct answer. This packet certainly will not be forwarded by a router. So that's a mechanism to force some traffic to stay link local. If you want to send some packets and you would to prevent those packets from going away from your local area network, then the very safe way is to put TTL or hop limit equal to 1. It may be forwarded by a bridge, because a bridge, as we will see, and that's a transition to what we will see in a minute, is transparent. So whether A and B are connected by a bridge or are on the same wires, A is directly connected to B using Ethernet cable, or whether there is a bridge in between, is invisible. Another way to think about it, a bridge is an intermediate system of layer 2, of the MAC layer, so it has no reason to be interested in the IP header. A bridge, in principle, does not understand the IP header. It looks essentially at one field, which is the MAC address. So a bridge is interested in the MAC address, to whom should I send this, and that's all. Whether it's an IP packet or not, in fact, the bridge, in principle, should not care. I say in principle because, of course, when you do a bridge, perhaps you want to do deep packet inspection or whatever reason, but what we call the architecture function bridge, in principle, should not do it. So that is the correct answer. Voila, that's the end of the IP module, at least for version 2. A bit later, we will talk again of a few other things that I call IP module number 3, which are serious violations, so things we should not do, but we still do. We have seen one, which is the NAT. We will see others later that are important. But for the time being, let's dive into the MAC layer. As this picture is showing, the MAC layer is about cabling. One of the issues when you do a computer network is to connect all the systems together. And cabling is a nightmare. I mean, even at home, when you have your PC or your Mac connected with a power supply, with a charger for your smartphone and perhaps a USB cable for your photo camera. I mean, as soon as you have more than 2 or 3 cables, they tend to do spaghetti plates here. So the MAC layer, we should really think of it as something that has been invented to solve a cabling problem. Of course, today the MAC layer is essentially wireless. We all use in this room Wi-Fi to communicate, and this is wireless, but it's a wire radio channel that is replacing the cable. But mentally, it is efficient if we think of it as the same thing, as a replacement for cable. So here, exceptionally, I will do a bit of history. I usually don't do it because we don't have enough time, and if you want to take the history of everything, the intermediate steps are perhaps less interesting as a first approach. But here, to really understand why the MAC layer is the way today, which many people consider as a nuisance, it's a complication of the internet architecture, we need to see how it has evolved. So MAC stands for Medium Access Control. And the problem that the MAC layer is solving, or was solving, as we will see today, things are a bit different, is this one. Imagine you are in the early beginnings of the internet. So at the early beginning of the internet, you would connect all the computers together with telephone systems. Then a bit later, you wanted to have special cables, And some people had the idea to use coax cable, the ones that are used for TV, and connect a number of computers. At that time, the computers were a bit like this, clumsy, heavy stuff. And you connect them to a cable that would go through the entire campus, as opposed to connect them to a telephone wires that would go to a central switching system. So some people had the idea of doing that. Good or bad, well, that was an idea. So the problem was to share this cable. Now, what is the problem? The problem is if you connect everything to the same cable, this is exactly the way we are connected to a TV distribution network. Except the TV distribution network in the old days was a broadcast medium where there's one source where you receive the signal through satellite dishes or rather antennas, and you feed the signal to everyone, and with your TV the only thing you do is to receive the signal. So it was a one-way medium and broadcast. The idea was to use the same cable but to allow two-way communication. Of course, if you allow two-way communications, you have new problems that arise. And the problems are if several systems talk together, then if we do nothing, we have a collision. If A sends a message and B at the same time sends a message, the two messages are sent over the same wires, and this might create chaos. Today we know how to solve this chaos using communication theory. We can find some methods of joint decoding, even if the two messages are sent on the same wire. If we know at least some information about the sender, the keys they're using, for example, for spreading the signal, we might be able to decode the two messages together. But that doesn't solve the problem. This is done typically on cellular systems where the cable is not a physical cable but a wireless channel. But that still requires that this guy that is decoding, or this guy that is decoding both, is actively decoding both. That means he's trying to tune to one or several of the other receivers. When the MAC layer was invented, none of those solutions were known, and what was known instead is the principle of mutual exclusion. That is the concept of distributed system. Mutual exclusion means that a number n of speakers are able to speak, and you want a way to make sure that only one at any given point in time is allowed to speak. So if A speaks, that should prevent B from speaking, or the other way around. Right? Only one system can talk at a time. Mutual exclusion is the way in which all the original cabling systems were done. If you use a telephone system, that means a central wiring system, instead of having this shared system we have here, then what was used was a polling system where the central place would send a message to a computer saying, now you can speak. The computer, if it has something to say, will respond with all the data it has to send, and then the central computer will poll the next device and ask for more data. This was, together with store and forward, this is how original networks were done. Here we don't want this. We don't want to grant access from a central arbiter that would say who can speak. Instead, we would like to have something distributed. We will find that this is a very strong idea that has evolved through the last 30 years. All computer networking solutions have been built with this idea of making distributed solutions to the problems. With SDN today, we see a wave going back in the reverse direction, where we centralize all the network functions into SDN controllers. But as we will see, we will always need a mixture of both. Distributed means that if A and B and perhaps C want to talk at the same time, there should be a way to implement mutual exclusion that is present in only ABC. Right? There is no other system involved. Now this is very, very frequently, you see it everywhere. So the thing we will see in detail is CSMA-CD, which is the mutual exclusion protocol that is used in Ethernet or in some versions of Ethernet. And this, with a large number of variants, exists in lots of similar things. Wi-Fi is very similar. Zigbee, if you talk to your light bulb instead of to your computer, you use a variant of wireless system that's lower power and lower range called Zigbee. If you use a power line to send your TV stream on your power cables, you will use a similar thing called home plug AV, for example, home plug MAC, or power line communication, PLC. They all are based on variants of the protocol that we will see here. There are very different things that were based on different mechanisms that we will not see that are essentially the token ring. The token ring was a way of bridging that was very, very popular in the 90s, but that is almost extinct now, that we will not see here. So Ethernet and all the variants are based on CSMA. So CSMA-CD exactly, which is practically synonym of Ethernet, derives from Aloha. So what is Aloha? Aloha means hello in Hawaiian language, and is the first radio network, computer network that was developed, and it was developed in the Hawaiian Islands. At that time, there was on one island one computer, and on several other islands there were other computers. It was in the 70s, right? It was developed independently of the internet and in parallel to the internet. Here, the communication was with radio frequencies, and there was one channel for one way of communication and another channel for the reverse direction. And it was centralized computing, store and forward. So there was a central thing on the main island, and on the remote islands you had peripherals. So communication from a remote to another remote was not possible. If you wanted to send a mail to somebody sending there, you would send it in a store and forward fashion, first to the central computer, and the central computer would now send it to the remote here. And the people who did it were very visionaries. They developed what is called a randomized algorithm. A non-randomized algorithm, the token ring way of doing it, would consist in saying this guy would poll each of the remote once in a row. So it would send a short message here saying, do you have something to send? This guy would respond, and we would do that in round, and it will go by rounds like this. This would be what is called a polling mechanism, and is more or less what a token ring does here. But here they wanted to have something more fancy, probably, and they decided to make something completely random that works in the following way. So the problem is only from the remote to the center, because there is a unique center. Whenever the center sends to someone, we don't need a protocol, because the center sends only one packet at a time. So if it has two packets to send, it will serialize them and send them in turn by looking at the destination. The problem is when data is sent from the remote to the center, because those two remotes could send at the same time. Since they are sending on the same radio frequency, that might well cause a collision. And with the decoding technology of that time, a collision means probably the two packets are lost. The two channels are not interfering, they're on different radio frequencies, so we're really interested in only the upstream channel. And then Aloha can be described by this simple algorithm. It simply consists in saying, when you have something to send, simply send. So you are optimistic. Usually it's bad to be optimistic. I mean, many people think it's better to be pessimistic. If there is a bad thing happening, you will be alive after if you're optimistic and a hurricane is coming, perhaps you will be dead. If you're pessimistic, you go away and you will survive. But here, be optimistic. You will lose a packet in the worst case. And the protocol says, when I send a packet, I expect the sender to return an acknowledgement. So I will see if I receive an acknowledgement whether this packet has been sent. Since the acknowledgements are sent by the sender on the reverse channels, the acknowledgements are never subject to collision. So I send, wait for an acknowledgement, and if I don't receive an acknowledgement, what can have happened? Well, it can be that there's a data error on the channel and the packet is lost, or that there is a collision. It's impossible to know which of the two, and the protocol interprets the absence of acknowledgement as a collision. So if there is no acknowledgement, then we try again transmitting. So that gives the algorithm. You try n max time, send the frame, wait for an acknowledgement or a timeout, so you wait for some time. If you've received the ACK, then the transmission is over, finished. If you have not received the ACK, the timeout will fire, you try again. And here we see that we wait for a random time before retransmitting. That's the only smart thing of this protocol. Why do we need to wait for a random time here? Yes?
If we are perfectly synchronized, the conflict will happen over and over.
If we are perfectly synchronized, the conflict will happen again and again. Even if we're not synchronized, the collision might cause a synchronization. If those two guys, by accident, have overlapping times, they will both sense a collision and will retransmit at perhaps the same time, depending on their propagation times. So there is a risk of a collision that repeats itself and you are in deadlock. So to avoid the deadlock, we wait for a random time. The deadlock will occur, but with a small probability. So that is ALOA. Now, if you do ALOA, you can show that it works poorly, in fact. If you assume the arrival of messages if you assume the arrival of messages here is completely random, the way to model something random is assuming they arrive as a Poisson process, then the throughput that you can reach, so the max rate at which you can receive messages and reliably deliver them, is order of 18% of the channel rate. So if you do simplifying assumption, assume the 4 channels here have the same transmission rate, say 1 megabit per second, for example, then the total throughput of the entire system will be only 180 kilobit per second, where in fact it has 4 links at 1 megabit per second each. So it's a very inefficient way, but it's very simple. It requires very little intelligence and therefore can be done with really unsophisticated hardware and software. Of course, this is not used today. It is used only in those situations where you're trying to bootstrap a communication and you have really no way of synchronizing. So it is used, for example, in the cellular networks when you set up the signaling channel. When your mobile talks to a base station, it must set up a channel. And while it is setting up the channel, someone else may be also setting up a channel at the same time. So during this phase, you use a protocol similar to ALOA, but this phase occurs very rarely. The next step was to do an obvious improvement, perhaps not so obvious because it has some deep implication, which consists in saying, listen before you talk, which is what you in principle are doing in this class. Right? So, and this is called CSMA. So CSMA is essentially the same as ALOA, but before sending, you listen whether the channel is free. If the channel is not free, it means someone else is sending, then perhaps it's better for you not to send. So you will do the same thing with the same random time, but you're blocked as long as you sense that somebody is sending on the channel. This listening is called sensing. This is why this is called carrier sense. Now, of course, while you're doing that, you're making an assumption that makes the system closer to our original MAC layer design goal. Here the assumption is if somebody is sending, you can hear it, which was not true in the original ALOA setting. If the island on the left is sending something, the island on the right might not hear it. The central station will hear it, but the island on the right might not hear it. So CSMA works well with the assumption that we have what is called transitive medium, which means that if A is sending, then everybody can hear it, which is probably true on the cable as long as the cable is not too long. And this is the requirement for Ethernet. Ethernet cables are not long-distance cables. They are maximum 1 kilometer at low data rate. And the cable must be such that if we send a signal here, the attenuation is small enough so that in the worst case, the guy that's the remote end can still perceive that something is happening. Now, quick question. If we have this system, are we avoiding all collisions or not? I close in 5 seconds. Oops. The correct answer is the majority vote is C, which is perhaps counterintuitive. Let's see why. CSMA will avoid many collisions, but there is always a window of vulnerability, which is shown in this example. Here I'm showing what is called a time-space diagram. I have on the horizontal axis space, and on the vertical axis, time. And I'm showing A that is sending some data at time t equals 0. The data propagates on the cable, and since the propagation time is not 0, as we have seen 2 weeks ago, the line is not horizontal, but it's slightly slanted here. Now, and assume the propagation time is 2, imagine microseconds. Of course, those are all extremely small numbers. Assume B sends at t equal 1, then B senses that the channel is idle. Right? And will send something, and that will create a collision. The collision will be created at points in space and time where the two colors intersect. So there will be a collision here everywhere. If it had sent a little later, we see that there would have been a collision in the middle of the cable, but not at A, for example. And this will always happen regardless of the parameters, because the propagation time from A to B is always non-zero. Even if it's very small, there is always a small time, which is the time between when A starts to send and when B starts receiving the signal from A. This time is always non-zero, so regardless of the bandwidth delay product, this may happen. So it's the curse of distributed systems. This is why distributed systems are difficult, is because the delay between systems is always non-zero. Okay, But this is how Ethernet and all other variants that I mentioned before are based upon. Now, they use a few additional tricks to make the system work, but the idea is that you use CSMA, and the period of time during which a collision can occur is very small, and will be very small if the area of the network is small. So we're talking here of technology for local area networks. So all we need is, in fact, a way to manage the collisions. So we accept that collisions can occur, that they are rare, that we can make sure they don't repeat and we are not caught in deadlocks. One way to do that is called CD, collision detection of Ethernet, that consists in saying that we listen. So while we have something to send, we wait until the channel becomes free. That means we listen to the channel, and when we sense that it's idle, we send the frame. And then while sending the frame, we continue to listen and wait until the end of our transmission occurs and see whether we can sense a collision. We can sense a collision if the signal we are decoding is not the signal we have sent, but there is something else that is being sent. If that happens, we decide that there is a collision, and we stop transmitting, wait for a random time, and retransmit here. We also send some jamming, but send jamming simply means make sure the collision is long enough, because this is all analog systems. I mean, deciding whether there's a collision or not is not something that you can decide. It's not a binary thing. We're not talking of bits here, but radio signals that you're analyzing. So if you have a collision that lasts for a nanosecond, you will not detect it, of course. So you want it to be long enough to be reliably detected. I'm illustrating this on this sequence of space diagrams. A and B ascending, and it's the same diagram as before. There is a small delay of vulnerability. Shortly before the end of this delay, B starts transmitting. Right. Now, A here, A continues to transmit and senses while transmitting, senses that there is a collision. So it will force the collision to be long enough by sending the jam bits. Now, B will also sense the collision. In fact, B will sense it much before A. So both A and B have sensed that there is a collision. And that's the main thing we want to reach. We want a distributed protocol that gives the same information to everyone. So here, we want that only A or B transmits. We let them optimistically do, but we want to recover the case where there is a collision, and we have to have a consensus that everybody agrees there is a collision. Now here, that's the case. Both A and B agree that there is a collision, so they will wait for a random time. This is a time taken by A, the time taken by B. The granularity of this time is such that the difference between T1 and T2 is much larger than the vulnerability period, so that when this guy times out, this one with very high probability is either timing out at exactly the same time and the collision will repeat. That happens with small probability and will not repeat it itself indefinitely many times in the future. So the most likely thing is this will not happen again. Here it is B that fired before, so B now senses that the channel is idle, transmits. Now when A is here, now depending on the variant, for the strict CSMA-CD, A at time T1 here will sense that the channel is busy and will not transmit until the channel becomes free. So the collision will be resolved here at the advantage of B. It can be shown that the performance of this is much better. The performance now depends on the bandwidth delay product of the system, but for systems that are local area networks with the parameters, sizes, and bit rates of Ethernet, we can reach order of 90% of throughput efficiency. There is still an assumption that is being made, that is illustrated here on this figure. Here the assumption is that the transmission must be long enough so that you detect all collisions that occur. I'm showing on the left here A that has a very short packet to send over a very large network. There's a collision. B has started transmitting the pink packet before A and creating a collision with A. But A transmits, listens, sees no collision, and is happy. Decide the packet has been successfully transmitted. Because at A, there was no collision. Right? However, if the packet is destined to C, for example, there is a collision. C cannot receive the packet because this one is overlapping with the packet of B. So CSMA-CD doesn't work in the case on the left. This is solved in the case of Ethernet by requiring that the transmissions are always long enough. So we should always be in that case. Long enough for Ethernet is 64 bytes. So every Ethernet packet should be at least 64 bytes, which given the size of an IP header of a TCP header is always the case, except if you use IPv4 with a very short ICMP message, for example, it could be less than 64 bytes, in which case you're asked to pad the message, make the message artificially longer by sending unnecessary bytes in the message to make it longer. Of course, the 64 bytes has to be combined with the bit rate and the length of the system. So old-style Ethernet, 10 megabit per second, has a maximum diameter of 1 kilometer on a single cable, 2 kilometers if we have repeaters, much less if we have higher speeds, but this quantity remains the same always. So that's the theory of Ethernet. And the Ethernet that I've explained is this one. The one you have when you use cables, coax cable, to connect your computers. It's increasingly difficult to find them. You can find them. You probably need a special adapter. And then you really connect by connecting physically to the device. So you can remove the insulator and the shield and drill a hole to connect to it. And this is how the very first networks were made. There are versions of that are also on twisted pairs. In that case, it's even easier to connect. You would simply remove the plastic around the pair. You connect in the middle with a T connector. That is Ethernet, and this is where Ethernet comes from. But admittedly, if we use Ethernet today, we probably don't see those things. But if we use Wi-Fi, we have a very similar thing. On Wi-Fi, everything is, like I said, plus a zillion of complications. I mean, the Wi-Fi standard is almost 3,000 pages, so it's very complicated. But the main complication is that the wireless channel is not transitive. If A sends to B, it's not certain that C will see that A is sending, depending where you are. I mean, there might be the power of this might be enough to reach B, but not to reach C, for example. Or there might be a wall, or the reflections might be such that it doesn't work. So the way the channel is made transitive in Wi-Fi is to send a short preamble to packets called the RTS-CTS, where in Wi-Fi, before A sends, it sends an RTS, request to RST. This is taken from the book, and this is there's a typo. It's an RTS, request to send, and the RTS is sent, and the B that receives it acknowledges it, but the acknowledgement is sent from B. So when B sends it, I mean, this shows that it goes to A, but it's sent in all directions. So C will see that A and B have started to send something. So, of course, during that period when you send the RTS, C doesn't see it, and there could be a collision that kills the RTS, but we minimize the duration of time during which this can occur. And let me conclude with this last poll. Seemingly simple, but important question. I close in 5 seconds. The correct answer is A. There is only one that can be sent at any point in time. And of course, this is true also for Ethernet. That's a mutual exclusion algorithm. So the goal of mutual exclusion is that only one can be sent at a time. It's also called sometimes a collision domain. Within a collision domain, only one packet is sent at a time. Voila. We do a break and resume the story of the MAC layer in 13 minutes at 1:15.